Alright, we're going to be talking about Euler's theorem, another major result in number theory. And it's a real mathematical beauty. Let's have a look at it together. Well, the claim. So, let A and B coprime integers. Then A raised to the power of phi of n, where phi is Euler's totient function, is congruent to 1 modulo n. Quite simple, very pretty. One can prove some very interesting results using this quite simply. And the proof is no less simple, especially since we now have the apparatus from the last video. Now, we shall begin by considering the product as the product of all those elements contained in the capital phi n, where the capital phi n is a set of all those of all integers totient to n. This means that it is the set of all those integers which are coprime with n and are greater than 1, or greater than or equal to 1. We observe, and this is the key step in the proof, that this is actually equal to the product of again, we are taking the product over all elements of capital phi n, but of f a of b. The reason for it is we have established in the previous video that fa, the function which we define as in the following fashion. Let us run a brief reminder. Fa of x is defined as ax modulo n. You observe that fa is a function which maps capital phi n into capital phi n, and we have proven that it is a bijection. So the equality holds because the isomorphism simply alters the position of the factors. And since multiplication is position invariant, we obtain equality. Now, we observe then that this is equal to, by definition, the product, again, over all elements of capital phi n, of a b modulo n. This is congruent to the same thing without the modulo. That's simply a change of notation. And now we observe that we can write this, because a is invariant, it's always the same. So we can factor it out, and thus we obtain a to phi of n. It is that n times. It's not that n times. It is the right thing to do. Let me finish writing this and I'll comment on it further. It is the right definition because by design, or by construction, it holds for all n that the cardinality of capital phi n is equal to lowercase phi of n. To verify this, one simply needs to read the definitions. It is quite obvious. And now we observe that on either side of the congruence, we are no longer dealing with equality because we have a congruence here. On either side of the congruence, we have this factor, or rather this term. So we can use the cancellation theorem to obtain that 1 is congruent to a phi of n modulo n. And also notice that we have used well the cancellation theorem because the product of all totients is coprime to n, of all totients to n is coprime to n. And like this, we have obtained the desired result. And this concludes the proof.